Hello friends, today we are going to discuss Booth multiplication algorithm, which is used to perform the multiplication of two signed numbers, and everybody knows the signed number is a number with some positive or negative sign. So in this algorithm we will see how the computer multiplies any two signed numbers where the data or the numbers are stored in some registers. So let's take one practical example for this. For example, there are two registers having the data, say register X is having the data -5 and register Y is having data +6. So now we need to multiply these two numbers. These numbers are obviously stored in some binary form in some registers. So when we multiply any two numbers, let's X and Y, so this X will be known as multiplicand and this Y is known as multiplier. So here we can see the multiplicand is in the negative form and the multiplier is the positive number. As the essential requirements of the Booth multiplication algorithm, we need few registers, standard registers. They are known as the AR, BR and QR. And obviously we will need one flip-flop that is known as QN+1. This AR in particular it will carry the zeros, and the number of zeros are equal to total number of digits in BR. So in BR we will take multiplicand and this QR will comprise of multiplier. And this QN+1 is a flip-flop. Now, what will be the value of BR? This is the major, this is the essential and one of the important step in this Booth multiplication algorithm. And majority of the students will do the mistake at this step. So we'll see how to calculate the value of BR. So 5 we can represent in binary as 101. This value 5 is negative. So negative numbers will be represented in the 2's complement form, and it will be equals to 1 1 0, and we represent this number in signed magnitude representation. So we will apply the sign bit, and after applying sign bit, this number will become 1011. So this will be the value of our BR, and we need also the value for BR complement plus 1, means the 2's complement of BR again, so it will be 1010. So these both values we will require during the algorithm. At which stage they will be required, we'll discuss later on. Now, how to calculate the value of this QR? So we'll see how to calculate this QR. In our case, the QR's value is 6. 6, the binary value of 6 is 1, 1 and 0. And since this 6 is the positive number, so therefore there is no need to take the 2's complement of this number again. But the sign is positive, that's why the sign bit we need to apply. And the sign bit for the positive number representation is 0, as everybody knows. So 0, 1, 1, 0. This will be the value of our QR. So we need this value also during the algorithm. So we'll see in the next slide what are the steps required to multiply these two numbers, although we have calculated the value of BR and QR. So we'll see in the next slide. So let me write the values. As we know, our the value of BR was -5. So the value was 1, 1, 0 and 1, and value for BR complement plus 1 was 1, 0, 1 and 0. Similarly, the value of QR was +6, and this will be represented as 1, 1, 0 and 0. Let's start the process. The few points we should remember during the multiplication process, especially in the Booth multiplication, we need to check the sign of Qn and Qn plus 1, Qn and Qn plus 1. This Qn is the last bit of QR, and Qn plus 1, as we have discussed, it is already a flip-flop. So if the value of Qn and Qn plus 1 is 0, 1, then the steps will be: first step, add BR, and the second step will be arithmetic shift right, AC or AR, BR, oh sorry, it's not BR, is QR, and Qn plus 1. And the third step will be reduce the value of counter by 1. Similarly, if the value of Qn and Qn plus 1 is 1 0, the second, in this case we will perform add br complement plus 1 instead of br. This is the first step, and the second step will be arithmetic shift right ar qr and obviously qn plus 1. And lastly, the same step again will follow, reduce the counter by 1. And in the last case, if the value of qn and qn plus 1 is either 0 0 or 1 1, then we'll perform the steps. There's no need to perform any addition. We'll directly perform the second step, and that will be arithmetic shift right ar qr and qn plus 1. And in the last, we'll reduce the counter by 1. So hope you are getting what kind of steps we are going to follow in this algorithm. Hope you will remember these steps. Now so hopefully everybody knows what is the meaning of arithmetical shift right. Again, I am just revising your concepts. ASHR is arithmetical shift right. What does it mean? Since we have to use this during this algorithm, that's why we should know how to calculate the arithmetic shift right of a number. So let there is a register R having the number 10011. So after performing arithmetic shift right R, we will get the value 1 0 0 1 and 1. Means after shifting, this value will again come at this place. Let's take one more example so it will be more clear to you. If the number is like this, then after performing arithmetical shift right, this 0 will come here after shifting, and this MSB will remain as it is intact. So 0 0 1 1 0. So this is how we will calculate the arithmetical shift right during the process of this Booth multiplication algorithm. So the next slide, we will see how the numbers get multiplied automatically by using this Booth multiplication algorithm. So if you are able to recall, our BR and QR values were, the value of BR was 1 0 1 1. BR complement plus 1 is 0 1 0 1, and QR equals to 0 1 1 0. So these things, so here our multiplication process starts. We will take AR QR, Qn plus 1, and the counter which will count the steps. As I've discussed already, the size of AR will depends upon the number of bits available in the BR register. So here the value of QR is 0110. Value of Qn, initially it will be 0. The number of bits in the BR are 4, that's why we'll keep 4 zeros in the register AR. And here the value of QR is 4 bit, that's why the value of counter will be 100, because 100 is the binary value of 4. So let's start with the process. This bit is known as Qn. This is Qn, and this is, this is Qn plus 1. So we'll test these two bits. So the first step is our Qn and Qn plus 1. As we can see, these are 0, 0. So the first step will be, if you remember the previous table, arithmetic shift right, AR, QR and Qn plus 1. So it will be 0, 0, 0, 0, 0, 0, 1, 1 and 0. And we will reduce the value of SC will be SC minus 1. So we will reduce the counter by 1 and it will become 0, 1, 1. So friends, we'll see how these bits are being shifted. So this 0 comes here, this 1, this 1, this 0, the 0 will come here, this, like this, and this bit will be shifted. So this is how we'll perform the arithmetical shift right during the algorithm. So we have completed our first step. For the next step, we'll again test the value of Qn and Qn plus 1, and we can see now the values of Qn and Qn plus 1 is 1, 0. At 1, 0, we will perform add BR complement plus 1. So, and we know the BR complement is 0, 1, 0, 1. So we'll add it 0, 1, 0, 1 and calculate the addition between these two numbers. So it is 1, 0, 1 and 0. Here the number remain intact. You can write it as, this will also remain intact. Now the next step will be arithmetical shift right and reduce the counter by 1. So perform the arithmetic shift right, 0, 0, 1, 0, 1, 0, 0, 1 and 1. Again, for its simplicity to understand, this 1 comes here, like this, and ultimately we will reduce the counter by 1. So here the counter will become 0, 1, 0. Here our second step also completes. Next step is, again we'll test the value of Qn and Qn plus 1, and this is, now you can see it's 1 1. So in case the value is 1 1, if you remember, we'll simply perform arithmetical shift right and reduce the counter. So perform arithmetical shift right, it will be 0 0 0 1 0 1 0 0 and 1, and reduce the counter, it will become 0 0 1. Hope you are getting. So again here you can see this one comes here, this is 0, this is again 0, this 1, this 0, this 1, this 0, this 0, and this comes here. Now the counter's value is still 1. So we'll continue this same process again and again till the counter remains greater than 0. So one more step need to be performed. So to complete the last step, again we'll test the value of Qn and Qn plus 1, and you can see now it is 0 and 1. So at 0 1 we'll perform add BR. At 1 0 we have performed BR complement plus 1 addition. Now we'll perform add BR. So let's add this number BR. The value of BR is 1 0 1 1. So 1 0 1 1. So perform the addition between these two numbers. 1 1 0 carry 1, 1 1 0 again carry 1, this 1, this 1, and this number remain intact. Now perform arithmetic shift right and reduce the counter by 1. So now we'll get 1 1 1 0 0 0 1 0 and 0, and the value of counter will now become 0 0 and 0. You can see the counter becomes 0. That's why we have to stop this process. And our final product will come in the two registers AR and QR. So let's rewrite the value of AR QR together here. AR and QR, it is 1 1 1 0 0 0 1 0. This is the value of our final product of the numbers -5 and +6. Since the numbers are having the opposite signs, that's why the final product will come in the 2's complemented form, and to get the actual result, again we need to perform its 2's complement. So after 2's complement we'll get the number 0 1 1 1 1 and 0 0 0. So let's calculate its decimal number. So we'll get the actual result. Its decimal number will be 1 2 4 8 and 16. 16 plus 8, it's 24 plus 8 plus 4, 28 plus 2, 30. So it is minus 30. So friends, we have multiplied number minus 5 with plus 6, and here we get the result as minus 30. So hope you have enjoyed this video. In the next video, we will see another example of booth multiplication algorithm, where we will change the numbers. We'll take either both the numbers in the negative form or both the numbers in the positive form, and we'll see how the results will come similar. And moreover, we will see the flowchart of the booth multiplication algorithm as well. So thanks a lot.